Hello.
Okay, yeah, we can get started now. So first, I'd like to introduce FASE very briefly. This is the Fabrication on Sculpting event. And today we're going to have 4 posters. Actually, one author couldn't make it today, so we're going to have 3 poster presentations. And these posters all have to do with something to do with fabrication, sculpting, art, and mathematics. And also, I'd like to pay a tribute to one of the founding members of FASE, Matt Friedman. He unfortunately passed away due to COVID-19 complications a month ago. Please read the tribute online that's available. Okay, so let's get started. I'm going to allow sharing just a sec. So I'm going to make the authors a co-host. So please, Christoph, if you could share your screen.
Of course, I will start. Can anyone hear me? I hope so.
Yes, yes.
Perfect. Can you also see my presentation?
Yes, looks good. So yes, so for our first speaker today is Christoph Schinkel. He'll be talking about the new grid-based mid-surface generation algorithm. Please go ahead.
Okay, hello, thank you for the introduction. As already mentioned, my name is Christoph Schinkel, and I will present to you today our work on a new grid-based mid-surface generation algorithm. Let me dive right into the topic and start with the question, what is a mid-surface? So a mid-surface is a simplified, idealized 2D surface lying mostly midway of a thin-walled cut model. So in a sense, mimicking its shape. That would be a rather general description. In our paper, we prefer the definition of a mid-surface being a non-volumetric, non-manifold polygonal representation of a solid volumetric CAD model, if it yields equivalent simulation results. So the correctness of any mid-surface transformation is heavily related with the given context. Typically that would be the context of physical simulation one wants to perform. For example, the reproduction of thermal and mechanical processing using the finite element method or the like. So here in this example, you see we have data from building information modeling on the left side, geometry of a building basically. And on the right side, a simplified mid-surface representation, which is in this case used for energy analysis. So this example illustrates the thin-walled output geometry you can see on the right side, which has the benefit of greatly reducing the computational effort for further analysis and simulations. So now let me guide you through our 4-step pipeline. Our algorithm takes a mesh, a triangle mesh, and 2 additional parameters as an input, basically 2 additional parameters. The parameters define the smallest and the greatest distance between 2 opposite surfaces that should be merged together. So, so this is the first step of the pipeline, which is called the voxelization, and it builds a sparse binary voxel grid. Basically by marking each voxel that has a non-empty intersection with the input surface geometry with a so-called one voxel. And in our image here, you can see the red lines resembling the surface of the object. And after voxelization, you obtain the light red voxels, the light red non-voxels. The second second stage of the pipeline is the kernel stage, where we apply a kernel to each of the voxels to basically generate a a weighted, denser representation of in our grid domain. So for each voxel, what the kernel basically does is it counts the number of one voxels in the neighborhood. So in our 2D examples, that would be the 8 neighboring voxels. In our in 3D, that would be the 26 neighboring voxels, or even more, depending on how large you define the kernel size to be. So what you see in our depiction here is that dark blue stands for a low number of neighboring one voxels, and red stands for a high number of neighboring one voxels. And when you look into the inside, basically, of the geometry, then you already get a glimpse of these orange and red voxels somehow resembling where the actual mid-surface will be in one of the consecutive steps. That brings me to the third stage of the pipeline, the vertex movement. The third step, the vertices of the input mesh are moved towards the voxel grid maximum. So this is an iterative process, and the vertices are moved one voxel at a time, basically. And this is done. This is done until no further improvement can be obtained, or until the path exceeds the greatest distance between two opposing surfaces, which is one of the input parameters. So in our example, you can see that the resulting surface, the resulting object, almost resembles a mid-surface, and it is only kind of interrupted by smaller cavities, which we try to get rid in the last step of the pipeline, the vertex clustering step, where the vertices are clustered using a mean shift algorithm, and they are to be merged, basically to remove the remaining cavities. Then what you end up with is basically a two-sided representation of the mid-surface, and by performing an additional topological cleanup step, you can obtain a one-sided mid-surface representation. So you can see in our example here that the clusters are depicted by the gray circles, and then you also see the final merged positions after applying the mean shift clustering. Here's an overview slide where you can see all the 4 steps, namely the voxelization, applying the kernel, moving the vertices, and then clustering the vertices to obtain the final mid surface. And last but not least, here's a result with a test object. On the top left, you see the input geometry, which is the form of a pipe T-junction. The picture in the top middle shows then the voxelized version of the pipe with sparse interior, so to say. And the picture on the top right, you can see the resulting grid after the kernel operation, where you can see the red, orange-ish voxels in the middle that are then used to shift the surface to obtain the final result. On the bottom row depicts on the left side a sparse voxel representation, of the final mid-surface, not the actual result of the third stage, because that would be very sparse depending on the amount of input triangles. So we decided to depict here a voxelized version of the third step. And on the bottom right, you could see the final result in gray. I hope you can see that. Yeah? And overlaid with the input geometry, so you can see that the resulting mid-surface lies midway between the thin-walled input mesh. However, what you can also make out is that we have shrinkage problems at the object boundaries. This can be seen at the mounting surface on the top where the mid-surface is slightly smaller than one would expect it to be. But depending on the simulation use case, this may not even present a limitation. However, we are investigating this in future work. We also have we are currently in a project with an industry partner that is investigating our approach, and the partner is performing structural analysis on similar parts. And the feedback so far we got is very positive, and we are quite eager to continue this work, which is at the moment a work in progress. So that's it from my side. Thanks for your attention.
All right, thank you very much. Excellent talk. This looks very nice. It looks pretty easy to implement as well. Are there any questions?
Hi, this is James Mallows. Is it the advantage of a grid base that it's a faster algorithm?
Yes, it is. I mean, depending on the size of the objects, of course, and the voxel grid resolution. It is also possible to parallelize many of the operations. So in that case, I would say it is the advantage of it being scalable.
To follow up on that question, the orientation of the grid probably matters. Have you experimented with random orientations?
No, this is also on the to-do list. This is something we definitely want to look into as soon as possible, because we also have these edge cases where it really depends on how these things are oriented in space. Maybe one could also, I don't know, try to apply machine learning like algorithms to obtain a good initial orientation.
All right. Are there any more questions? Okay, thank you very much.
Thank you.
And now we have the analog randomizer by Jack Tate. Please share your screen.
Okay. Oh, wow, where's it gone? Oh no. Oh, shit. Hello?
Hello, cool. Please go ahead.
I'm not sure what's happened. I've got the screen sharing on and I'm ready to do my presentation, but I don't see any more of the other participants.
It might be, you might not be able to see the participants when you are sharing your screen.
Okay.
We can only see half of your screen though.
Well, I've got a presentation ready here.
Okay.
Can you see that now?
We can all see it. Yes.
That should be filling, with any luck, it should be filling the screen.
Yes, it is.
Okay.
It looks good.
Fine. Thank you very much. So shall I start now? Is everybody sorted out?
Yes, please. So
Okay.
This is Dr.
Fine.
Jack Tate talking about his analog randomizer.
Hi, I'm an artist living in Wales and took my PhD in analog drawing machines at the ripe age of 77. And I've got increasingly interested in random graphics. And I'm more and more interested in chaos. I've done papers in near chaos, and I want to go further. So I set about building a randomizer to take the step from random, from quasi-random rather to random. And there are subtle distinctions between random and quasi-random, and also between chaos and near chaos. So we have to deal in subjective things. And as this is an art thing, there's no such thing as a mathematical proof. And the other thing that I'm very interested in is coherence in the image. It's the aesthetic notion that there's something like Hamlet and Polonius were talking about clouds in the Hamlet thing, that is based on what we see and what we perceive. And I've also become interested in, however far I go to chaos, there does seem to be the persistence of determinism, which is probably partly to do with the nature of the analog machines. Just to set the scene, these are some early images where there was a balance between determinism and quasi-randomness. And I got more and more interested in the effects on this image here. And I built a machine to take this further. I'd also noted that other pictures from other machines were displaying characteristics of randomness, such as here. And this is a light drawing where there's randomness appearing. So this sets the scene for what is happening with the other machines that's done in the PhD. A lot of the work has been involved in an asynchronous pen. This is without any pen lift, but this is getting nearer to chaos when the pen lift is working out of synchronization, out of phase, and it starts to get involved in chaotic or semi-chaotic effects. Can I just check that you can see the whole screen at the moment, or is it clipping?
Right now, we can see it, but sometimes it is clipped.
Okay, I'll try and keep it a little smaller for you. These are the machines that I've been using. There's a regular plotter on the left-hand side, an X-square plotter, with a programmer, which you can see here, which is a sequential programmer. And part of the problem is that however much you program the sequences, they're always fixed and they don't change. And in order to go further and take the research to another dimension, I wanted to go further than quasi-randomness, which was built into the machines. And this machine here was built to try and push the boundary of graphics into chaos as far as I could. So it's a machine that originally made in the 70s, and I've done a recent machine in the last few months to try and extend the boundaries. And this is another turntable machine where I put as much inbuilt quasi-randomness in the machine that I could. So it's part of a preoccupation with near chaos. And I've written 2 papers for international journals on that. This is the encouraging from earlier work where there were elements of moving towards chaos, particularly on the right, and some more work here where the results of plotter using without a pen lift on the left, and there are 3 things it can do. You can go north, south, east, west, or draw circles. But when you introduce a pen lift into the system, you get an even more chaos. I'm sorry that this keeps jumping about. I'll bring it down to here. And the pictures that you see here are introducing, again, quasi-randomness into work with light drawings, which is programmed straight into a digital camera. So all in all, the work must move towards near chaos. So finally, I decided to build a machine. It's very crudely simple, as you can see, but it in fact spins a flywheel, a couple of flywheels, a small flywheel and a large one, and the timer pulses the motor to spin this, and it ends up randomly on any one of 6 outlets. And so the first thing that I was interested in is to try and look at the nature of lines. And I wanted to try and make the chance of a line which was chaotic in itself before going on to other drawings. And this was a successful chaotic line in my view. And so it encouraged me to continue and use the randomizer on an XY plotter. Now, I've said earlier that the differences are subtle, but what the randomizer gave me here, because there are 3 outlets for single points and 3 outlets for joint ones, and on the XY plotter, when X and Y go together, that gave me the chance of diagonal lines, which I didn't get before on the plotter. So that was a step in the right direction. And this was another program which the randomizer put into the XY plotter. Again, coming back to the persistence of determinism, there's still, because of the nature of an XY plotter, there's still results in it hanging on there. With the new drum machine, things were able to push further towards chaos, where coherence begins to disappear. And this was using a pen lift, which adds to the chaotic nature. And there's a picture here without. And when I got to this stage and writing the paper, I felt that I'd gone beyond the coherent images and gone into a territory which was, in my view, had reached chaos. And the amount of coherence is virtually non-existent. So the justification for building the random machine as opposed to quasi was justified. So that's the end of the presentation, and I can go back and answer any questions now with any of the pictures that people wish to pose to me.
Thank you very much.
Do I stop sharing now, or do I keep the sharing going?
I think please keep the share for now.
Jack, I love the artwork, and the more chaos, the better. I'm not sure you've taken it all the way where it isn't visually
What are
interesting.
you referring to, by the way? I'd like to answer your question, but which is the one that you're latching onto?
So yeah, I guess the question is, I mean, your most random results are not as random as like interference on the old TV screens, where
No,
I think
they're
everyone would
not.
say there's nothing here. I don't know, maybe you should poll your viewers and see if they see something in these new results.
Well, I'd like to have some feedback, because it is purely evaluation is, as has been said, it's in the eye of the beholder, and this is something that we can't measure. Everybody will see something different, so feedback from the viewer is of paramount importance. But could you tell me which one you are particularly commenting on?
Actually, I think it's the one that's on the screen now, centered.
That one, this one. Is that the one?
Yes, yes.
Well, I feel that's lacking coherence, and that it is distributing chaos in terms of analog graphic drawing machines, and quite different from the mix that I've had in the past. And this has gone a long way from making an image which has got any aesthetic quality. But again, this is a debate because it's subjective.
Okay, thank you.
I have a question. In one of the earlier figures with the colors.
Can I go back to it? You tell me to stop when I get to the picture you want to talk about.
Yes. Okay. Keep going, please. I think it's page 8. On the bottom there.
Ah.
Okay.
So
on page 8.
I can't see the page number at the moment on my.
Okay, this one, yes. Are those colors random, or are they painted in afterwards?
What happens is that the drawing machines make the drawings, and then they're scanned, and the colors are put in intuitively in Photoshop.
Okay.
So they're not, if this were digital, then I would be able to program the computer to throw a dice, as I did with the Hewlett-Packard years and years ago, and put in the color randomly, but it's not. It's seat of the pants flying totally intuitively. It's not according to any particular algorithm.
I think they look very nice. Are there any other questions? Okay, thank you very much.
So shall I stop sharing a screen now?
Yes, please.
Okay, thank you. Thank you very much indeed.
Okay, and then for the final presentation today, we have James Malice, a sculptor from Washington, DC. So please share your screen.
Okay, just a sec.
All right, please go ahead.
Is that working?
Yes.
Okay. Hi, everybody. I'm James Mallows. I'm a sculptor in Washington, D.C. And I'm very happy to be here. Sorry, we're not actually in Strasbourg. My talk is toward fabricating surfaces as patchworks of pantographic lattices. If you're familiar with the term grid shell in architecture, basically a pantographic lattice is the same thing as a grid shell. So the historical basis of this idea goes back to Chebyshev in a talk he gave in Paris in 1878 on the cut of clothing, or on the cut of clothing, and he surprised everyone with showing an informal proof that you can dress the hemisphere with just an ordinary sort of tablecloth that's been cut according to the grid of the, I guess I'm not able to use my mouse on this, but that's okay. According to the grain of the fabric into this sort of rounded square, and it would actually drape onto the sphere without any sort of wrinkles or folds. There's basically two ways you can put the Cartesian grid onto a smooth surface. The conformal net is probably more familiar, where we keep all the angles the same, but we can change the lengths any way we want. And then what is now called the Chebyshev net, where we don't worry about the angles, but we keep the intervals between the intersecting grid curves the same distance as measured on the surface. And then there's a discrete version that's a little easier to play with, where you don't worry about measuring distance on the surface, but just between 2 points in space. So on the left, you get an idea of what it would be like to drape that tablecloth on a hemisphere. And also, you get an intuitive sense of what Chebyshev informally proved, that you can build one of these nets starting at any point on a smooth surface and given two crossing lines. And you can maybe picture using a compass to start to lay out those intersections between the points, again, as a discrete measurement, not on the surface, but directly through space. So that's he was interested in the draping of cloth. He'd actually done some consulting on making military uniforms. That's what brought this idea to his attention. If you don't use something as flexible as cloth, but stiff like a wire mesh, this kind of an exciting transformation goes on. You cut your mesh out flat on the plane, and you can shear it in the plane, like A as it is cut, B it's sheared in the plane, it's still perfectly flat. But if you constrain the perimeter of that patch of wire mesh, it suddenly pops into a very smooth surface not a complete closed surface, of course, but a patch. And it's really kind of a fun thing to play with, a little piece of screen material like this, because the curves are just perfectly smooth to the eye. Even though they don't have to be spherical, if you squeeze it different ways, you get more like a paraboloidal surfaces. It's fun, at least from a sculptor's point of view, it's fun. And so our idea that we want to explore here is, how do we use this shape changing in normal 3D printing to make little models and things that might be made in a class or in a makerspace? So we're late to the party because architects have been interested in this idea at least since 1967, when Frei Otto built his first sort of prototype of what's called a grid shell. And these are all slats that are actually straight, and they start out lying flat on the ground. And the whole structure can rotate about the crossing points. And so that gives it that same freedom that the fabric has to accommodate a different shape. And a grid shell is typically lifted up or maybe pushed up by inflation from the bottom. And then the edges of the grid shell are restrained. And at that point, you have something like a straw hat that is a definite shape, but it's still, it's sensitive to asymmetric loading. A point loading would make, as you would expect from a straw hat, start to buckle in and maybe buckle out at distant points. So from the architect's point of view, and we're not going to worry about this, they need to lock all of those crossings with either a bolt that uses friction to lock it, or actually putting in extra members that diagonalize all those quads. And they also have to worry about how to make them watertight. So we're not going to worry about those two problems. We're not going to worry about resisting asymmetric loading. We're not going to worry about how do you make something that's watertight, airtight. There must be solutions to that. So that's the architects. Now the metamaterial engineers that are interested in using microfabrication to make materials with new properties are also looking at the same idea, in their terms, pantographic lattices, and I think that's a little more explanatory, so that's why I've used it. What you see on the right is actually a 3D printed large-scale model of what might be a future metamaterial, and it combines a lower layer of rods with little vertical columns, I hope you can see, and then a crossing layer of rods on top. And it works pretty well as a pantograph. So what I want to look at is, can we use this idea of little patches that can start flat and become a patch of a curved surface and patch them together to make at least interesting sculptures, maybe something practical. I don't know, obviously there's certain problems. But the idea is to be able to use a small 3D printer, such as a school or a makerspace might have, to, with very little time, make something large. And part of that, the bargain in that is there has to be some hand assembly. This thing isn't going to just pop out of that little 3D printer. It's, someone's going to have to print several patches on the build plate of that printer, but that can go very quickly. So it's possible that, say, 6 or 7, maybe more patches could be done in an hour, and then assembled at the user's leisure without tying up the machine. So what would we have to do that? We need to make those lattices fast. I despair of trying to make that metamaterial lattice very quickly with a 3D printer, because mainly the columns and the unsupportedness of the rods. So we need a way to make the lattices fast, and we have to anticipate hand fabrication. An easy way to the important thing is to constrain the perimeter of each patch so it takes the curvature that we're hoping for. And they also have to be attached together. Another hand process. So this is my first attempt at trying to get a fast lattice, was to just skip the vertical columns, just use hopefully a very small weld between 2 layers of rods. And I played a lot with the speed and the temperature, but I couldn't get any better results than you see in the picture. And you can tell that when I try to shear this patch, it overwhelms the stiffness of the rods. The stiffness of the welds is just too great. And so it as a pantograph, it doesn't propagate very far. Everything bends. It's not supposed to be curved. It's supposed to be, just change the angles, but keep the line straight. And also you can see when the little rod is delaminated, it's really a tight thing between getting it to have any kind of freedom of movement without actually wanting to fall apart. So here's an idea that works better. And this is only realized with a 3D pen, so it looks very primitive. But the idea is that you retrace each line in this grid, and when you're crossing over a perpendicular rod, you lift the extruder, and when you're retracing over a collinear rod, you push down and make a good weld. The point of that Z-hop, and it was a change in vertical position of the extruder, the purpose is to delay the mating of the two pieces of plastic. One is hot, one is probably cooled down to the bed temperature. And you can delay it enough that it makes a very weak weld or no weld at all. And yet when you push down on a collinear piece, you make a pretty good weld, a good enough weld. So you end up with a non-woven fabric that has a lot of ability to act as a pantograph. And I think this is actually going to work. Now let's move on to that hand fabrication step. This is a traditional saddlebag from a century or more ago, and they were using a chain stitch to close up their saddlebags. It's sort of like the original zipper in that piece by piece, as you pull a loop through these eyelets and then pull the next loop through all the way to the end, you'll gradually make a closed top, or basically sewing the top of the bag, but it's very easy to do by hand. And then at the very last, I don't know if you can see it all the way over to the right of the screen, there's actually something to put a padlock on this, because it's used, you need something that can hold that last loop. It needs to be locked in place. So it's always an issue. The last stitch has to be held in a different way. I imagine that could, since we're 3D printing, it could be anything, some sort of a clip, some sort of a hook, even could be integrally made with the same piece. So not a big problem. So what I envision the patches are like is that at the end of each, at the edges of the patch, there are loops that have each been sized for the purpose. And in a relatively quick hand process, it might use a crochet hook or something. All these loops can be chain stitched like that, except for the last, and that's going to have to be held in a different way or go on to stitching around some other part of the construction. So this would constrain that parameter and force this, this 3D printed grid up into a three-dimensional curvature. And the same technique, simply being extended, can also join the patches together, because when, let's say the one on the right has been made first, as the one on the left comes around, it can work its chain stitches through the other chain stitches. It's kind of a familiar fabric process. So you end up with a solid seam where the patches join. One nice thing about, see, we're going through these, we're basically doing this seam twice. We do once to constrain one of the patches, and a second time to constrain the other at the same time that we interlock the two. So that sounds like extra work to go twice on each seam, but in fact, it works out that there's always a simple closed tour that can double cover the seams in a patchwork. And it's not true. Of course, if you try to just single cover seams, you end up in dead ends and a lot of starting and stopping. So in some ways, this is an advantage. And this is how it would work. You model your patchwork of seams as an embedded graph. pick a spanning tree and then roadblock all of the edges that are not in the spanning tree. And then if you make U-turns at all the roadblocks, you see there is a path that meanders through, and it's for some of the seams, it's only going halfway and turning back, but in total, the whole thing is one big loop. And that solves the problem of not having to start and end at more than one place and not having to lock more than one stitch. So that's the basics. Obviously, it's kind of a young idea that isn't very well developed at this point, but I'm hoping to get back in touch with my 3D printer as the lockdown is released and make some real models. So I can take any questions.
Thank you very much. Are there any questions? I can start with one.
Okay.
You said that you had trouble with the 3D printed lattice because I think because they were not flexible enough at the joints. So because they were missing the vertical columns.
Yes.
Have you considered using some sort of water soluble support material so that rather than using a pen, you could print something with gaps in them, and then they should be able to turn. Or
I think that's a good idea, and it's probably the ultimate solution to really making a high performance grid. I didn't have access to a machine where that was going to be possible, and I would like to keep it as simple as possible as a technique. But I'm sure that would improve performance and make it possible to actually, you wouldn't have to just use a cylindrical filament. You could, since that crossing would be protected from forming any sort of weld, you could have any sort of structural member that you'd like. That really would be the best way. You're right.
are there any other questions? Okay, well, we look forward to your 3D printed results next year.
Okay, thank you. I'm having some trouble stopping my sharing.
Thanks to everybody. And then thanks, Shin, for a great sharing.
All right, thank you very much.
Thank you.
And this will conclude our FASE poster session. So we hope to see you next year. Thank you.
Thank
See you. Bye-bye.
Thank you. Bye.
Thank you.